Jupiter is not the planet you learned about in school, and we finally have proof. Juno's ultra-precise gravity measurements have let us weigh the inside of this 318 Earth mass giant, and the result completely destroys the old idea of a calm gas envelope wrapped around a neat little core. In this video, you'll see how we X-rayed a gas giant from hundreds of millions of kilometers away, what that revealed about Jupiter's hidden heart, and why that new picture doesn't just change one planet, it changes how we think every giant world in the galaxy is built. But before we continue, please subscribe to the channel to give your support. Let's continue. Jupiter is not just a bright thing in the night sky. It is a physical monster of a planet, about 140,000 kilometers wide, roughly 87,000 miles, and holding the mass of 318 Earths in one place. If you were falling toward it, you would not be drifting past pretty cloud bands. You would be dropping into a gravity well that helped decide which planets in the solar system even survived. That scale matters because a planet this massive does more than sit there looking impressive. It shapes orbits, it redirects asteroids and comets, it stirs the whole disk of gas and dust where planets form. So a simple question: if Jupiter's gravity had that much control over the early solar system, how much control did its hidden interior have over the final layout, including where Earth ended up? For a long time, the answer in your head was probably simple. You were told one of two options in school or in popular science books. Either Jupiter has a solid, compact core, a neat ball of rock and ice maybe 10 to 20 times the mass of Earth, sitting in the center like a seed, or Jupiter has no real core at all, just hydrogen and helium, getting denser and more exotic as you go down, but basically the same material all the way to the middle. Those two pictures sound very different, but they share the same idea: clean structure, either a clear rock core plus gas envelope or a smooth, coreless gas ball. And for decades, both pictures could hide behind the same excuse: we do not have precise enough data. Jupiter is too far, too big, too complex. So pick the model you like and wait for better measurements. Then Juno arrives, and this is where things start to break. NASA throws a spacecraft into a tight polar orbit around Jupiter, flying low over the cloud tops, tracking tiny changes in its motion with extreme precision. And suddenly, those old interior models do not just look a bit off, they simply do not fit the numbers. Here's the twist: the gravity field Juno measures is not consistent with a small, sharp, dense core, and it's not consistent with a coreless planet either. When scientists run the math, when they try to build an interior that reproduces the gravity harmonics Juno sees, they are forced into a third option, one that basically nobody grew up with. In that option, Jupiter does have a core, but it's not a tight ball. It's extended and diluted. Heavy elements, all the stuff heavier than helium, are spread out through a huge inner region, maybe 30 to 50% of the planet's radius. So instead of a tiny central lump a few thousand kilometers across, you get a deep zone, 20 to 35,000 kilometers thick, 12 to 22,000 miles, where hydrogen and helium are thoroughly mixed with rock and ice material. People call this a fuzzy core or a diluted core, but the key point is straightforward. There is no sharp boundary between core and envelope. The transition from heavy, mixed material to more pure hydrogen happens gradually. Densities and compositions change smoothly, layer by layer as you go deeper. Your old mental picture of a crisp center is gone. So what does that region actually look like in simple terms? It's not a hard surface, not something you could stand on. The pressures are in the millions to tens of millions of atmospheres. The temperatures are tens of thousands of degrees, hotter than the surface of the sun. Under those conditions, hydrogen is not a familiar gas. It's a dense fluid, and then a metallic liquid with electrons moving freely. Inside that fluid, elements like oxygen, silicon, iron, and water components are dissolved, mixed on a microscopic level. So the core is more like an ultra-dense metallic hydrogen mixture that happens to be loaded with heavy elements. Now, you could say, all right, neat detail, but this still sounds like deep trivia. Why should you, sitting on a rocky world 800 million kilometers away, care whether the middle of Jupiter is a compact ball or a fuzzy region spread across half the radius? The reason is this fuzziness tells you Jupiter's life story, and by extension, it tells you a lot about how planetary systems build themselves. If Jupiter had a clean, untouched core, you could argue for a fast, simple formation. Grow a solid core, then pull in gas. Keep the heavy stuff locked down. But if heavy elements are smeared out through a large inner fraction of the planet, that means they were mixed, redistributed, maybe even dissolved out of an original core over time. That points to slower growth, repeated impacts, ongoing mixing, a much messier process. That process doesn't only change the core, it changes everything Jupiter does. A fuzzy core affects how heat moves from the deep interior to the atmosphere, how fast the planet cools, and how much internal energy it can pump into its weather. It affects the properties of the metallic hydrogen layer that generates the magnetic field, and it affects how Jupiter's gravity was distributed when the solar system was young, which changes how it scattered planetesimals, the small building blocks of planets. There's also a larger cosmic reason this matters. In exoplanet surveys, Jupiter-like planets are everywhere. You see hot Jupiters hugging their stars, warm Jupiters further out, super Jupiters with even more mass. When you realize that your own Jupiter probably has a fuzzy core, you suddenly have to treat that as a common pattern, not a weird exception. The structure of Jupiter's interior becomes a template you use to interpret the masses and radii of exoplanets, to decide how much heavy material they hold, and what their formation history might have looked like. By the end of this deep dive, you should be able to describe Jupiter's interior in plain numbers. You should be able to say, near the cloud tops, the pressure is about 1 bar and the temperature is about 165 Kelvin, around minus 108 degrees Celsius, minus 162 Fahrenheit. And as you go down, pressures climb into the millions of atmospheres. Hydrogen turns metallic, temperatures rise to tens of thousands of Kelvin, and inside that extreme environment, maybe 7 to 25 Earth masses of heavy elements are distributed through an extended inner region, giving you a core that is real but not solid and sharp. You should also be able to say why scientists are confident in this picture, even though nobody has ever seen the core directly. We do not have photos, we have gravity measurements, magnetic field data, and constraints on how much water and other elements are in the atmosphere. All of that feeds into interior models, and the models that match the data best are the ones with a fuzzy core. The simple, compact core and coreless models just do not line up with Juno's numbers anymore. So the obvious question is, if you cannot send the camera down there, if any probe you drop would be crushed and vaporized long before it got close, how do you get these details? How do you turn tiny changes in a spacecraft's motion into a three-dimensional picture of Jupiter's unseen interior? And how do you know that picture is not just guesswork? To answer that, you have to look at what Juno actually did in orbit, how fast it moved, how close it flew, and how small a tug in its speed scientists were able to measure, because that is the trick that turned Jupiter from a mysterious gas ball into a mapped, weighted, and seriously constrained planet. How do you X-ray a planet you can never land on, never drill into, and never see below the cloud tops, but still claim you know what its core looks like? You do it by throwing a spacecraft at it on an orbit that is frankly a little insane. Juno does not cruise around Jupiter in a wide, lazy circle. It dives in on a stretched polar orbit that takes it just a few thousand kilometers above the clouds at closest approach, and then swings it far back out again. At periapsis, when it's closest to the planet, Juno is moving at about 209,000 kilometers per hour, around 130,000 miles per hour. That's roughly 170 times faster than a rifle bullet. This speed is not for show. It's how you get a clean gravity signal. You want to swoop right through Jupiter's strongest gravitational grip and feel every tiny change in that pull. The orbit is polar for a reason. It goes over the North Pole, then down past the South Pole, then back again, instead of hugging the equator. That way, Juno samples gravity at all latitudes. It feels how the planet's pull changes from band to band, belt to belt, pole to pole. And because the closest pass is only a few thousand kilometers above the visible clouds, you get a very strong, very sensitive interaction with Jupiter's mass. If Juno flew much higher, you would blur out the details. Fly much lower, and you risk frying the spacecraft in radiation and atmosphere. So this trajectory is a tight, dangerous line between data and death for the mission. But speed and orbit alone don't give you a core. The key is, how do you turn that motion into numbers? How do you extract information from a spacecraft that is just falling freely in a gravity field? Juno itself does not feel gravity in the way you do standing on Earth. It's in free fall, weightless. So you need a way to measure how Jupiter is tugging at it moment by moment. That's where the radio tracking comes in. Juno continuously beams a radio signal back to Earth over a distance of roughly 650 million kilometers, about 400 million miles when the geometry lines up. Deep space antennas on Earth listen to that signal and measure its frequency. When Jupiter's gravity speeds Juno up or slows it down along the line between Jupiter and Earth, the frequency of the radio tone shifts slightly. This is the Doppler effect, the same basic effect that changes the pitch of a passing siren. But here it's happening in radio, not sound. The important part is how small those shifts are. Scientists are measuring changes in Juno's speed as tiny as 0.01 millimeters per second. That's 0.0001 meters per second. Slower than your fingernails grow, slower than a glacier creeps. But with stable clocks and careful analysis, those tiny tugs are visible in the data. You get a time series of how Jupiter's gravity is accelerating and decelerating the spacecraft along its orbit. Every close pass adds more detail, more constraints on how mass is arranged inside the planet. Of course, gravity changes with time is not yet a picture, so the next step is to translate those raw speed variations into something you can actually interpret. This is where the language gets a bit technical, but the idea is straightforward. You describe Jupiter's gravity not with one number, but with a set of coefficients called harmonics that tell you how gravity changes with latitude and depth. The even harmonics, labeled J2, J4, J6, and so on, describe how the planet's mass is distributed in a way that is symmetric between north and south. J2 is mainly about how squashed the planet is at the poles, because Jupiter spins fast and bulges at the equator. J4 and J6 probe deeper details of how dense the interior is at different radii. The odd harmonics, like J3 and J5, are different. They capture asymmetries, differences between north and south, and are mostly linked to deep atmospheric flows rather than static structure. Before Juno, those harmonics had big error bars. You could fit many different interior models to the same fuzzy data. But Juno's precision improved the gravity field by roughly 2 orders of magnitude. That is about 100 times better than older missions. Once scientists had that level of accuracy, something interesting happened. When they calculated what J4 and J6 should be for a Jupiter with a compact, solid core, the predicted numbers did not line up with the observed ones. The measured J4 and J6 were smaller than expected for a dense lump at the center. To make the model match the data, you have to change how mass is distributed inside. Specifically, you have to move some heavy elements outwards, away from a sharp sensor, and smear them through a larger inner region. When you do that, when you allow the inner 30 to maybe 50% of Jupiter's radius to have a gradual change in composition, heavy material mixed into hydrogen and helium instead of locked in a ball, the calculated harmonics shift, and suddenly the theoretical J2, J4, J6 line up with Juno's measurements. Different research teams, using different assumptions about how hydrogen and helium behave at high pressure, kept hitting the same conclusion: extended diluted inner region, not a neat core. So why does gravity care where the heavy elements are? Because gravity responds to mass and where that mass sits. If all the heavy stuff is in a small central ball, you get a very steep increase in density toward the middle. That gives you one pattern of harmonics. If instead the heavy elements are smeared out through a big chunk of the radius, the density gradient is softer, more gradual, and the harmonics change in a specific way. Juno's data basically says the real Jupiter looks like the smeared case, not the sharp one. The only way to avoid that conclusion would be to say that all the physics of hydrogen and helium we use is completely broken, and lab experiments and simulations do not support that. If this sounds abstract, you can compare it to what we do with Earth. On Earth, we learned about the core using earthquakes. Seismic waves travel through the planet, and seismometers record how fast they move and how they bend. From that, you infer where the material gets denser, where it changes phase, where the liquid outer core ends and the solid inner core begins. You never see the core directly, you just see how it affects waves you can measure. With Jupiter, you do not have earthquakes and you cannot plant seismometers, but you can use Juno as a test mass and gravity as the probe. Instead of watching waves, you watch orbits. You see how Jupiter's interior makes Juno accelerate and decelerate along its path. The principle is the same. Infer what you cannot touch by watching what it does to something you can measure very precisely. The result is a kind of gravitational seismology, where each harmonic, each tiny coefficient, is a clue about how much heavy material is down there and how far out it extends. The surprising part is not that we can do this. The surprising part is that the data are now clean enough that simple, compact core models are no longer compatible. The old textbook picture is not just uncertain, it is ruled out within reasonable assumptions. So if the gravity field forces you to accept that heavy elements are diluted through a big inner region, the next question is, what is that region actually made of? What does a fuzzy core look like in real physical terms? What phases of matter live there? How many Earth masses of heavy elements are mixed in? And how sharp, or not, is the transition between that inner zone and the metallic hydrogen around it? How can something be a core if there is no solid surface, no sharp edge, nowhere you could even, in theory, stand? When you hear the word core, your brain goes straight to Earth. Iron and nickel, radius about 3,500 kilometers, roughly 2,200 miles. Clear boundary between mantle and core. You cross that line, everything changes. Simple, clean, done. Jupiter completely breaks that expectation. The thing we are still calling a core behaves nothing like a ball of metal inside a rock. The models that actually match Juno's gravity data say this: heavy elements are not locked in a tight central sphere. They're mixed with hydrogen and helium in a deep inner region that stretches out to somewhere between 0.3 and 0.5 of Jupiter's radius. So not a kernel a few thousand kilometers across, but a zone 20 to 35,000 kilometers deep, around 12 to 22,000 miles. That's a huge fraction of the planet. And that entire region counts as core in the new sense, because that's where the heavy material is concentrated. So instead of thinking ball in the middle, think inner zone where the composition is different. The deeper you go, the more heavy elements mixed into the hydrogen and helium. The outer layers are mostly light gases. The inner region is the same elements plus a rising load of stuff like oxygen, silicon, iron, the ingredients of rock and ice, all dissolved into the fluid. There's no sudden jump, there's a gradient, step by step, as pressure and temperature ramp up. That raises the obvious question: what is the material itself like in there? Because it's not gas the way you know it on Earth, and it's not rock the way you know it either. In the fuzzy core zone, pressures reach into the millions of bars. That's millions of times Earth's sea level pressure, and temperatures hit tens of thousands of Kelvin. So think above 10,000 up to maybe 30,000 or 40,000 Kelvin, hotter than the surface of the sun. At those conditions, hydrogen first becomes a super hot, dense fluid, then transitions into a metallic liquid. Electrons are free to move. It conducts electricity very well. Inside that metallic hydrogen, the heavy elements are not sitting as boulders or crystals. They're dissolved, broken down into ions and atoms mixed through the fluid. So the core material is basically metallic hydrogen and helium loaded with these heavy ingredients. Chemically, it's closer to an ultra-dense alloy than to any familiar rock. It's not a lump you can dig into. It's a deep region of exotic fluid, extremely dense, extremely hot, and extremely conductive. Then comes the next practical question. How much heavy material is actually involved? Interior models that respect Juno's gravity harmonics, plus what we know about Jupiter's proposition from its atmosphere, point to around 7 to 25 Earth masses of heavy elements in that diffuse core region, out of a total Jupiter mass of about 318 Earth masses. That means somewhere between 2 and maybe 8% of Jupiter's total mass is made of material heavier than helium. That may sound small, but in absolute terms, it is huge. Even the low end, 7 Earth masses, is 7 entire Earth's worth of rock and ice material mixed into that inner zone. The upper end, 25 Earth masses, is like stuffing almost 2 Neptunes worth of heavy elements into Jupiter's deep interior. And that is just what lives in the fuzzy core region, not counting any extra heavy elements that may be mixed further out in smaller amounts. Now, here's where Jupiter really refuses to behave like Earth. On Earth, you can draw clean boundaries: crust, mantle, outer core, inner core. Each transition is relatively sharp. Densities jump, phases change, you can define borders. In Jupiter, the story is much softer. The envelope of mostly hydrogen and helium gradually becomes richer in heavy elements as you go deeper. The temperature and density increase steadily. Somewhere inside, there may be a small innermost part, maybe just a few Earth masses, that is more concentrated and somewhat core-like in the traditional sense. But it is surrounded by an enormous transition region, the fuzzy zone, that blends smoothly into the metallic hydrogen above it. So in practice, there is no single radius where you can honestly say, here the core stops and the envelope begins. Any line you draw is somewhat arbitrary, based on how much heavy material you want to count as core. That is a big shift in thinking. You are no longer talking about clean layers stacked like an onion. You're talking about a chemically graded interior where composition, density, and temperature change together, gradually, from the outer hydrogen envelope down to the deepest heavy element-rich zone. This is exactly why the old formation models take such a big hit. The classic picture of core accretion said, build a compact solid core of around 10 Earth masses, then once that core gets big enough, gas accretion runs away. Jupiter grabs hydrogen and helium from the disk fast, and you end up with a giant planet that has a hard, untouched core buried under a mostly uniform envelope. Mixing between core and envelope was assumed to be limited. The core stays sharp, the envelope stays cleaner. Juno's fuzzy core picture does not fit that at all. You are now looking at a planet whose innards have been stirred and partially eroded. Heavy elements are not neatly trapped, they are spread outward through a huge volume. That means one of two things, and likely both. Either Jupiter's formation was slower and allowed more time for solids to dissolve and mix into the envelope as they came in, or later processes like ongoing convection and possibly impacts gradually ate away at an original compact core and smeared its material outwards. Either way, the old simple story, solid core first, clean gas later, almost no mixing, is broken. Not by opinion, but by the fact that its predictions for the gravity field do not match what Juno actually measured. The interior is chemically structured, partially eroded, and dynamically complex, and that forces you to upgrade your mental model of what a giant planet core even is. So if the core is fuzzy, graded, and mixed, and if 7 to 25 Earth masses of heavy elements are dissolved into metallic hydrogen instead of sitting in a solid ball, What does that do to the extreme pressures and temperatures there? And how do those conditions further blur the line between core and envelope, turning solids and ices into strange phases of matter? How extreme does it actually get inside Jupiter, in real numbers, not just very hot and very dense? Start at the top, right at the visible cloud layer. There, the pressure is about 1 bar, basically the same as Earth's sea level pressure, and the temperature is roughly 165 Kelvin, around minus 108 degrees Celsius, about minus 162 degrees Fahrenheit. That is cold enough that ammonia and other gases can freeze into crystals. It looks turbulent and violent in images, but physically, that layer is still a low-pressure, low-temperature part of the planet. Now move downward, even just a few hundred kilometers, and both pressure and temperature start to climb fast. The exact profile depends on details of the atmosphere, but the trend is simple. Every step inward adds more gas above you. More weight, more compression. By the time you're thousands of kilometers down, the pressure has already jumped far beyond anything we can experience directly on Earth. The gas is thicker, hotter, and squeezed, and you are still nowhere near the real extremes. The big structural change happens when you reach the metallic hydrogen zone, roughly between 20,000 and 60,000 kilometers below the visible clouds. That's about 12,000 to 37,000 miles of descent. In this band, pressures are in the millions to tens of millions of atmospheres, millions of bar, and temperatures rise above 10,000 Kelvin, up into the 10,000 to 18,000 Kelvin range according to current models. At this point, hydrogen has been forced into a state where its electrons are no longer locked to single atoms. They can move freely through the fluid. In plain language, hydrogen stops behaving like a normal molecular gas and starts behaving like a liquid metal. It conducts electricity very well, better than many metals at room temperature. And because Jupiter is rotating and convecting, this metallic hydrogen is moving, rising, sinking, shearing, all while carrying electric currents. That combination of motion and conductivity is exactly what you need for a dynamo, the process that generates a magnetic field. So this layer is a key part of why Jupiter's magnetic field is about 10 times stronger at the cloud tops than Earth's field at the surface, and why its magnetosphere is large enough to engulf the sun. Keep going down, closer to the fuzzy core region, and the numbers get brutal. Near the diluted core, models that fit Juno's gravity data suggest pressures of roughly 3,000 to 4,500 gigapascals. That's 3,000 to 4,500 billion pascals, or in more intuitive terms, around 30 to 45 million bar. That means 30 to 45 million times Earth's surface pressure. At the same time, temperatures are estimated to be in the 20,000 to 36,000 Kelvin range, so up to 6 times hotter than the visible surface of the sun, which is about 5,800 Kelvin. If you want a physical sense of that pressure, think of taking the weight of a huge number of heavy objects and concentrating it. A common way to picture it is the force on each square centimeter would be like the weight of thousands of large animals all focused on a tiny area about the size of a fingertip. That's the kind of crushing load we are talking about, far beyond what any material on Earth could withstand in a normal lab setup. Under these conditions, materials you think of as solid, like rock, metal, and ice, don't behave the way they do at the surface of Earth. At tens of millions of bar and tens of thousands of Kelvin, they are likely in fluid or partially dissolved states, mixed into the metallic hydrogen. Their atoms and ions are part of the same high-pressure soup. So instead of a clean, solid core wrapped in a fluid envelope, you get a deep region where everything is mixed and blurred. That's a big part of why the core is fuzzy in the first place. This is also where phase diagrams become important. A phase diagram is just a map that tells you what state a material is in, solid, liquid, gas, plasma, under different combinations of temperature and pressure. For water, we know that diagram very well. For hydrogen, helium, silicates, and metals at Jupiter core conditions, we are still working it out. High-pressure experiments with diamond anvil cells and powerful lasers can only reach parts of that diagram for very short times, and ab initio simulations, the big computer models that work from quantum mechanics upward, fill in the rest. Small differences in those diagrams change whether a given material melts, dissolves, or separates at a given depth, which directly affects how fuzzy the core looks. So these extreme conditions do not just make good trivia, they actively drive the structure. If rock and ice stay solid, you might preserve a compact core. If they tend to dissolve into metallic hydrogen at multi-megabar pressures, the core material will gradually spread outward, eroding the sharp boundary and building exactly the kind of diluted, graded inner region that Juno's gravity data seems to be demanding. The physics of matter at 30 to 45 million bar is not just a footnote, it is the engine behind the entire fuzzy core concept. There's also a practical reason to care about the units you use when you talk about all this. Metric units, pascals, bars, Kelvin, kilometers, are what go into the actual equations. When scientists calculate hydrostatic equilibrium, how pressure balances gravity, or plug in equations of state to see how density changes with depth, they work in SI units, pressure in pascals, distance in meters, temperature in Kelvin. That is where the precision lives. But to feel how extreme these numbers are, the imperial system and everyday comparisons can help. Saying millions of atmospheres is roughly like saying you stacked more than 10,000 kilometers, about 6,200 miles, of Earth's oceans on top of your head. Pressure at the bottom of the deepest part of Earth's ocean is already a crushing value, only around 1,100 bar. Jupiter's interior multiplies that by tens of thousands. When you mix those two ways of talking about it, you get both the exact numbers that go into the models and the gut sense that this environment is completely outside normal experience. The key point is these pressures and temperatures are not side details. They explain why Jupiter's core cannot stay as a neat rock sphere. They force materials into strange phases. They encourage dissolution and mixing, and they create the conditions for metallic hydrogen dynamos and fuzzy composition gradients. So once you accept these numbers, you're almost forced into the new picture of Jupiter's interior. That leaves one big challenge. How do we know we are not just guessing the right numbers? How do we tie these extreme conditions and this fuzzy structure back to hard observations? In other words, what specific data from Juno actually broke the old compact core models and pushed everyone toward this messy, graded interior? How do you know that this fuzzy core picture is real and not just some clever artist's impression that happens to sound cool? The short answer is, Juno made the gravity data so precise that the old models could not hide anymore. Before Juno, missions like Pioneer, Voyager, and Galileo gave us a basic gravity field, enough to say Jupiter is squashed at the poles, enough to estimate a rough interior, but the uncertainties were large. You could build a compact rock core model or a mostly coreless model, and both could sneak through the error bars. Juno changed that by improving the gravity measurements by about 2 orders of magnitude, around a factor of 100 in precision. That is the scale of the jump. Suddenly, tiny mismatches that were invisible before become obvious, and when you try to fit the old, neat core structures to Juno's numbers, they just don't land on the right values. The gravity field of a spinning planet like Jupiter is encoded in numbers called zonal harmonics, J2, J4, J6, and so on. J2 tells you how much mass is concentrated toward the equator versus the poles, basically how much the planet bulges because of its rapid rotation. J4 and J6 dig deeper. They respond to finer details of how density changes with radius and latitude. If you think of J2 as the broad shape, J4 and J6 are more like the fine print about the interior. When scientists took Juno's ultra-precise data and computed these even harmonics, something jumped out. J4 and J6 were smaller than what compact core models predicted. If you build a Jupiter with a small, dense, untouched rock core and a relatively uniform envelope above it, you get a certain pattern of J2, J4, J6, and Juno's measured J2 was fine. But J4 and J6 came out off, too low in magnitude compared to those clean core calculations. To bring the theoretical J4 and J6 down to the observed values, you have to change the density structure. That means lowering how sharply density jumps near the center. The way you do that is to spread some of the heavy elements outward into a bigger inner region, instead of keeping them locked in a tight central ball. In practice, you adjust the interior model so that the heavy element fraction increases gradually over a wide zone. And when you do that, the computed harmonics shift toward the Juno values. The fuzzy core is not a stylistic choice. It's what you're forced into when you try to match J4 and J6 at Juno's precision. But there's another layer of complexity. Jupiter is not a static ball. It has deep winds and jet streams, and those moving masses also affect the gravity field. This is where the odd harmonics like J3 and J5 come in. The even harmonics mostly care about the static north-south symmetric parts of the planet. The odd ones pick up asymmetries, features that differ between north and south, and those are strongly linked to deep blows in the atmosphere. Juno measured those odd harmonics too, and the results told you something important. The jets you see at the cloud tops, those banded winds, don't stop right at the visible surface. They extend downward thousands of kilometers. But they also don't go all the way through the metallic hydrogen layer. They fade out at some depth. That separation matters because it lets you disentangle what part of the gravity signal comes from weather and what part comes from the deep static interior, including the core region. So you have two sets of clues. The even harmonics, mainly about the interior's mass distribution, the odd ones revealing how far the winds reach. Next comes the hard part, turning those coefficients into an actual density profile. This is an inverse problem. You're given the output, the gravity field, and you need to find the input, the distribution of density and composition that would create it. In practice, teams build thousands of interior models. They assume a certain equation of state for hydrogen and helium, which tells you how dense the fluid is at a given pressure and temperature. They specify how much heavy material is in different layers and how far inward or outward the composition gradients stretch. Then they calculate what gravity field that interior would produce and compare it to Juno's measured harmonics. If it doesn't match within the uncertainties, that model is out. If it does, it survives to the next round. What is striking is that multiple independent groups, using different hydrogen-helium equations of state, different numerical methods, and different assumptions about details, keep converging on the same broad picture. To match J2, J4, J6, and the constraints from J3 and J5, you need a diluted, extended inner region rich in heavy elements, not a tight, sharply bounded core. The exact numbers, like whether the heavy element mass is closer to 10 or 20 Earth masses, can differ between models, but the qualitative structure, fuzzy, graded core, keeps showing up. This is why planetary scientists say we finally know what Jupiter's core looks like, and not just maybe. Before Juno, the parameter space for interior models was huge. You could tweak densities, move heavy elements around, and still sit inside the error bars. Now, with Juno's gravity data, plus its magnetic field mapping, plus measurements of water abundance in the atmosphere, the allowed space shrank brutally. Many of the old, simple models are just ruled out. They fail hard against at least one set of observations. The fuzzy core is not a fringe idea anymore. It is the default starting point. If you want to propose a radically different interior, you now have to show, step by step, how your model reproduces all the measured harmonics, the magnetic field features, and the composition constraints. That is a high bar. And so far, the models that pass it all have the same key features: an extended inner region, mixed heavy elements, and no sharp core envelope boundary. So once you accept that the gravity data has locked in this fuzzy structure, the next logical question is, what exactly are those heavy elements? How much of them is water or ice? How much is rock and metal? And how are they distributed between the deep interior and the atmosphere? Because that composition is the direct clue to what kind of solid material Jupiter ate when it was forming. How do you actually figure out what Jupiter is made of when all you see is the top few dozen kilometers of clouds? You start with the simplest thing you can measure directly: the composition of the atmosphere. You look at how much carbon, nitrogen, sulfur, and the noble gases there are compared to the sun, and you see something immediately. Jupiter's atmosphere is enriched in these elements by roughly a factor of 3 relative to solar. That means per unit hydrogen and helium, you get about 3 times as much of the heavy stuff. That alone tells you Jupiter did not form from pure gas. It swallowed a lot of solid material, ices, rocks, metals, during its growth. Those elements do not come in as pure gases. They come locked in planetesimals, in icy and rocky bodies, the building blocks of planets. When Jupiter formed, it had to grab not just gas from the disk, but also these solid chunks, melt them, and mix their material into its envelope. So when you see 3 times solar carbon or nitrogen in the outer layers now, you're basically seeing a chemical receipt for how many solids went in. That is already a strong hint that Jupiter's interior holds a significant mass of heavy elements. Water is the other major clue, because water carries oxygen, and oxygen is a big part of the heavy budget. The problem is, you can't just point a camera and see water deep down. Clouds and weather complicate things. This is where Juno's microwave radiometer comes in. It probes below the visible clouds by looking at microwave emissions, and from those, it can infer water abundance in the near equatorial region. The numbers are not one single value. They fall in a range, roughly 1 to 5 times the solar water abundance. But even that range is gold scientifically. If Jupiter has around solar water, that means one thing about how many icy planetesimals it accreted. If it has several times solar, that means it grabbed a lot more ice, and therefore a lot more oxygen. Juno's measurements tell you that Jupiter is at least not depleted and may be significantly enriched in water compared to the Sun. So again, you're seeing evidence for a big heavy element intake during formation. Now you take these atmospheric enrichments, 3 times solar for many elements, 1 to 5 times solar for water, and you plug them into formation models. These models simulate a growing planet sitting in a disk, pulling in gas and solids over time. You ask, how many Earth masses of heavy elements would Jupiter need to accrete and then mix at least partly into its envelope to end up with the compositions we see today? When you do that consistently, you land in the same ballpark that the gravity-based interior models gave you: total heavy element masses of about 10 to 30 Earth masses. Not all of that is in the fuzzy core region, but a large fraction is. This is a nice cross-check. Gravity data on one side, atmospheric composition on the other, and both push you toward a Jupiter that contains maybe 10, 15, 20, up to 30 Earth masses of material heavier than helium. This agreement is one of the reasons scientists are confident they are not wildly off. The next important point is not just how much heavy material there is, but where it lives. If you still had the old picture, you'd pack almost all of those 10 to 30 Earth masses into a compact rock and ice core, and the envelope above it would be mostly clean hydrogen and helium, with maybe a light seasoning of heavy elements. But the fuzzy core scenario says something different. A large fraction of that heavy material is spread through a deep interior region, blended into the metallic hydrogen, not locked in a concentrated ball. That spatial distribution matters for the planet's behavior over billions of years. If heavy elements are spread out, they create composition gradients, layers where the mixture slowly changes with depth. Those gradients affect convection, the process that moves heat from the deep interior towards the surface. A strongly mixed homogeneous interior would convect efficiently, moving heat out fast. A graded interior with heavier material gradually increasing downward can slow convection, make it layered or double diffusive, where heat and composition don't mix at the same rate. That in turn changes how fast Jupiter cools, how much internal heat it still leaks today, and how much energy is available to drive its weather. Remember, Jupiter radiates more energy than it gets from the Sun. That extra energy comes from its interior, leftover formation heat and slow contraction, filtered through this fuzzy, compositionally structured core region. So where the heavy elements live is directly tied to how bright and active Jupiter still is. The magnetic field also cares about this distribution. The metallic hydrogen dynamo needs fluid motion and good electrical conductivity. Mixing heavy elements into that region changes density, viscosity, and conductivity, which can tweak how the dynamo operates, how strong the field is, how asymmetric it becomes, and why Juno sees weird flux patches and an offset magnetic dipole. You don't get those details right if you pretend the heavy elements are all sealed up in a tiny central rock ball. What you're really doing, step by step, is reverse engineering the building blocks Jupiter formed from a few key numbers: gravity harmonics, atmospheric enrichment ratios, water abundance. You work backwards to the composition of the early solar system solids. You ask, how many icy planetesimals? How many rocky bodies? With what kind of mixture of water, ammonia, carbon-rich material, and silicates had to fall into Jupiter to build up 10 to 30 Earth masses of heavy elements and produce the 3-times solar enrichments you see now? When you find a set of building blocks that reproduces those observed ratios and also fits the gravity data after billions of mixing and evolution, you have a self-consistent story. That story says Jupiter didn't just sip gas from the disk, it actively ate a lot of solid stuff, broke it down, and mixed its material into a fuzzy core and envelope instead of keeping them neatly stacked in a cold, untouched rock center. Jupiter's current composition is a fossil record of that messy feeding history. So now the tension ramps up. If Jupiter clearly contains this much heavy material, and if that material is diluted through a big inner region instead of trapped in a compact core, what does that say about the classic formation theories, the clean core accretion picture and the disk instability shortcut? Can either of those standard stories survive this new interior, or are you forced into a new, messier, hybrid explanation for how a giant planet like this actually comes into existence? How do you build a planet this huge, end up with 10 to 30 Earth masses of heavy elements inside it, and still not get a clean, solid core at the center? The standard story you probably heard is core accretion. In that picture, you start with a disk of gas and dust around the young sun. You slowly glue dust grains into pebbles, pebbles into kilometer-sized bodies, and those into a growing protoplanet. Over a few million years, you assemble a solid core of roughly 10 Earth masses, mostly rock and ice. Once that core hits a critical mass, its gravity becomes strong enough to pull in gas from the surrounding disk very efficiently, so it rapidly accretes hydrogen and helium until it reaches something like Jupiter's current 318 Earth masses. In this simple version, most of the heavy elements end up in that compact core, and the envelope above is mostly clean gas. The rival idea is disk instability. This one takes a shortcut. Instead of slowly building a core first, it says a patch of the gas disk itself becomes gravitationally unstable and collapses directly, forming a giant, mostly gas object in one go. More like a tiny brown dwarf than a core plus envelope planet. In that scenario, you do not start with a big rock and ice core. You start with a clump of gas, and any solids you pick up later are a bonus, not the main feature. The interior should be much more uniform, with little or no dense core at the center. These two stories sit at opposite ends of a spectrum. Core accretion gives you a strong, compact core and a distinct envelope. Disk instability gives you a mostly coreless gas ball. And for a long time, both could claim Jupiter because the data were fuzzy enough that you could tune parameters and make either one look plausible. The fuzzy core that Juno forced on us is bad news for both simple versions. A classic, untouched core accretion result with a tight 10 Earth mass rock core that never really mixed does not fit the gravity harmonics. It produces the wrong J4 and J6. It makes the density jump near the center too sharp. The data say the inner 30 to 50% of the radius has a gradual composition gradient, not a clean step, so that neat compact core has to be at least partially erased or diluted. On the other hand, a pure disk instability planet, basically a gas clump with little or no core, also fails. It does not naturally give you 10 to 30 Earth masses of heavy elements and the 3 times solar enrichments in the atmosphere. A direct gas collapse would mostly reproduce the composition of the gas in the disk, which should be close to the sun. You wouldn't automatically end up with that much extra rock and ice mixed in, unless you then add a lot of solids later anyway, which pushes you back towards something that looks like core accretion plus mixing. So you're stuck in the middle. The data say there was significant solid material involved, enough to build at least a core seed and enrich the envelope. But they also say that core did not stay crisp. It got partially dissolved, partially mixed, and spread into a wide inner region. You're forced into a hybrid story. There was a core, but it didn't survive in the simple form you were taught. The interior you see now is the result of both initial assembly and billions of years of evolution. Recent work on formation tries to resolve this by making the growth of Jupiter slower and messier. Instead of a clean two-step process, build core then grab gas, you let the planet accrete solids and gas together over an extended period. Heavy planetesimals don't just stop at the edge of a hard core. They plunge deep into the envelope. They heat up, they melt, and in many cases, they dissolve directly into the metallic hydrogen before they can reach any solid center. Their mass and elements get mixed into the inner envelope, not parked neatly at the bottom. If that happens over millions of years, you naturally build composition gradients. The deeper regions get more and more loaded with heavy elements, because that's where the dissolved material tends to settle. But you never get a razor-sharp boundary. Some material may collect in a denser innermost part, but above that you keep a long transition zone. This is exactly the fuzziness you see today. A broad inner region, 0.3 to 0.5 Jupiter radii, where the heavy element fraction increases steadily with depth. You also have to consider that Jupiter was forming in a dynamic disk full of other bodies, embryos and planetesimals. It may have migrated inward and outward, changing what kind of solids it could eat over time. Some simulations suggest that as Jupiter moved, it swept up different populations of icy and rocky objects, each batch with its own mixture of water, ammonia, carbon compounds, and silicates. All of that variety ends up blended imperfectly into the fuzzy core and envelope. So the chemical gradients you infer today may literally be the layered fingerprints of those different feeding phases. In this view, the core is not just a structure you draw on a diagram. It's a fossil record. The detailed shape of the fuzzy region, how far it extends, how sharply the heavy element fraction rises with depth, how much heavy material is in the very center versus in the outer part of the fuzzy zone, all of that encodes history. If Jupiter's core is very extended and heavily mixed, that points to long-term dissolution and strong mixing. If it were more compact, that would point to a shorter, cleaner formation. There's also room in some models for large impacts, big bodies with several Earth masses slamming into early Jupiter and dumping material deep into the interior. Those impacts would stir the planet, heat it, and help redistribute heavy elements. Whether they're necessary or just a dramatic extra on top of the slow, messy accretion is still debated. But in any case, the interior today remembers that violence, just not in a way you can see with your eyes, only in the gravity and composition profiles. So when you look at Jupiter now and you think about this fuzzy core, you're not just seeing what the planet is. You're seeing a frozen history of how it grew, how much solid material it consumed, how deeply that material sank, how thoroughly it was mixed, and how much of any original compact core survived. That's why nailing down the core structure is such a big deal. It reaches back to the first few million years of the solar system and tells you, in hard numbers, how chaotic or gentle that era really was. But this immediately raises another sharp question. If mixing and slow accretion can dilute a core over time, do you also need a single catastrophic event, a giant impact, to shatter an original solid core and spread its fragments? Or has that dramatic idea been oversold, and the fuzziness is better explained without a one-time crash? The idea that really grabbed attention a few years ago was very simple and very dramatic. Maybe Jupiter's fuzzy core is not a slow process at all. Maybe it's the scar of a single huge collision. In that scenario, early Jupiter forms a fairly compact core, Then a mini-planet, a protoplanet with something like 5 to 15 Earth masses, falls almost straight in and hits it head-on. The impact is so energetic that it shatters the original solid core and mixes the heavy material into the inner envelope. You go from a sharp core to a diluted one in one go, more like a tiny brown dwarf than a core plus envelope planet. In that scenario, you do not start with a big rock and ice core. You start with a clump of gas, and any solids you pick up later are a bonus, not the main feature. The interior should be much more uniform, with little or no dense core at the center. For a while, this was attractive because it gave you a clear, one-time mechanism to erase a compact core. You start with something that looks like the standard core accretion outcome: dense center, clean layers, then one big crash ruins the neat structure, spreads heavy elements out over a big fraction of the radius, and leaves behind exactly the kind of extended, heavy element-rich region that Juno's gravity data seemed to require. It felt like a clean way to bridge the gap between theory and observation. High-resolution simulations made this idea look physically plausible. People ran smoothed particle hydrodynamics (SPH) simulations, where they model both the early Jupiter and the incoming protoplanet as swarms of particles that obey gravity and fluid equations. In those models, a fully head-on impact with the right math and speed can indeed disrupt the central core. The heavy material from the impactor and from Jupiter's original core get mixed into the surrounding hydrogen and helium, and you end up with heavy elements spread through a big chunk of the inner planet. The simulations also showed that Jupiter does not necessarily get destroyed in the process. It can remain bound and resettle into a stable giant after the collision. So for a while, you could tell a nice story. Jupiter formed a compact core, then something big, maybe a 10 Earth mass body, hit it dead center, shattered the core, mixed the heavy material, and left a fuzzy core as a long-term relic. You still needed to think about how that structure evolved over billions of years, but at least you had a direct and efficient way to break the original core. However, as people pushed this idea further, combining n-body simulations of how planets actually move and collide in a forming system with impact modeling and long-term thermal evolution, some issues started to show up. First, the geometry. The orbits you expect in a real protoplanetary disk give you mostly oblique impacts, not perfect head-on. Grazing collisions are far more common than direct center punches. Oblique impacts don't penetrate as deeply, and they're less efficient at smashing a central core and redistributing material through the whole inner region. So the perfect head-on case may be the exception, not the rule. Second, the long-term thermal story is tricky. A collision that big dumps an enormous amount of energy into Jupiter's interior. It heats the planet strongly, and that heat has to go somewhere. If you spread the heavy elements out into a huge inner region and add all that energy, you then have to evolve the planet for billions of years and see whether you can end up with something that matches Jupiter's current radius, luminosity, and interior structure. Some studies find that it is hard to keep such a wildly extended fuzzy core stable over the entire age of the solar system without overheating the planet or letting the composition gradient smooth out too much. Put simply, when you combine realistic impact angles, orbital histories, and thermal evolution, the single giant impact explanation starts to look less clean. It is not impossible, but you need a fairly specific sequence of events, and you still have to fine-tune how mixing, cooling, and re-stratification play out. It stops being the simple one-click fix-it first appeared to be. Meanwhile, newer simulations of planet formation that do not rely on a single huge collision are getting better. These models track how a growing Jupiter accretes both gas and solids over time. Solids in the form of planetesimals and pebbles can be dragged deep into the envelope by gas drag, can break up, and can dissolve into the fluid layers before ever reaching a sharp core. If that happens consistently over a long growth phase, you automatically get a deep region enriched in heavy elements. The fuzziness comes from continuous mixing and gradual erosion, not a single catastrophic event. In these newer models, the core may start out relatively compact, but as more and more solids rain in and partly dissolve at different depths, the boundary between core and envelope becomes blurred. Convection can be inhibited by composition gradients, so instead of fully homogenizing the interior, you build a layered structure, with heavy element concentration increasing smoothly toward the center. That is exactly the kind of graded interior the Juno gravity data points to, and you get it without needing a rare, perfectly aimed giant impact. The emerging view right now is that Jupiter's fuzzy core is more likely the product of its entire formation history: slow to moderate accretion of gas, continuous feeding of solids, partial dissolution of an initial core, and long-term mixing under extreme pressure and temperature. The giant impact scenario is not completely dead, but it looks less necessary and less favored than it did when it was first proposed. Fuzziness from formation and evolution seems to do the job on its own. This shift changes the way you picture Jupiter's early life. Instead of one cinematic boom that instantly transforms a neat core into a diluted one, you get millions of smaller events, countless planetesimals and embryos falling in, their ices and rocks broken down and absorbed into a metallic hydrogen ocean under crushing pressures. Over time, that process builds up the 10 to 30 Earth masses of heavy elements we infer today and spreads them through a large fraction of the interior. Less Hollywood, more cumulative chemistry and physics, but the final state, a strange, graded, diluted core, is the same. And this slow, layered mixing story doesn't just stay trapped deep inside the planet, because as soon as you start talking about composition gradients and partial mixing, you're also talking about how heat moves, how convection works, and how far the deep motions that drive Jupiter's weather can reach. So the next question is sharp. If the core is fuzzy and the interior is stratified, what does that do to Jupiter's jets, storms, and internal heat engine that powers the clouds you actually see? How far down do Jupiter's storms actually reach? And where does the hidden core start to control what you see in those cloud bands? The stripes you see in telescope images look like surface features, thin paint on a sphere, but Juno's gravity and microwave data say otherwise. Those jet streams, the bright and dark bands racing east and west, are not just skin deep. They extend roughly 3,000 to 5,000 kilometers down, about 1,900 to 3,100 miles, below the visible clouds. That is deep compared to the thickness of the weather layer you can see, but it's still shallow compared to the full radius and the 20,000 plus kilometer deep metallic hydrogen region. The key point is those jets are deep enough that they feel the interior, but they don't punch all the way into the fuzzy core region. The gravity signal Juno measures tells you that the jets fade with depth. Their influence on the gravity field drops off, and below a few thousand kilometers, the planet's rotation looks more like a solid body, almost like a more uniform spin. That means the core and the weather are dynamically linked because the jets sit on top of a massive rotating interior, but they're not the same system. The fuzzy core isn't being shredded by the winds, and the winds don't directly churn the core. Look at the most famous storm, the Great Red Spot. It's easy to think of it as a flat whirlpool painted on the cloud tops, but Juno has tracked how it affects the gravity field and how its microwave signature changes with depth. Those measurements suggest the red spot extends roughly 500 kilometers below the visible cloud tops, about 300 miles. That's shallow compared to the tens of thousands of kilometers down to the metallic hydrogen and fuzzy core, but it's still far deeper than any storm system on Earth. Even at 500 kilometers depth, pressure and temperature are higher than at the cloud tops. The gas is denser, and the storm is tapping into heat from below. It's not just being driven by sunlight on the surface of the clouds, so the deeper interior, including how heat leaks upward through the stratified layers, still matters for how long a structure like the red spot can survive, and how much energy it can draw from the planet. To see how the fuzzy core changes things, you have to talk about convection in plain language. Convection is just hot material rising, cool material sinking, like water boiling in a pot. In a planet with a homogeneous interior where the composition is almost the same everywhere at a given depth, convection can run very efficiently. Hot fluid rises, dumps its heat, cools, and sinks again. That process can move enormous amounts of energy from the interior to the outer layers. In Jupiter, the fuzzy core introduces a composition gradient. As you go deeper, the mixture has more and more heavy elements dissolved in the hydrogen and helium. That means deeper layers are not just hotter, they're also intrinsically denser because of composition. Even if you heat a parcel of fluid, its extra heavy element content can keep it from rising as easily into lighter, cleaner layers above. This competition between temperature effects and composition effects can slow convection down and break it into layers. This is where the idea of double diffusive or layered convection comes in. Heat and composition don't mix at the same rate. Heat can move relatively quickly, heavy elements move more slowly. So you can get a staircase structure. Thin layers that are well mixed internally, separated by sharper composition jumps that resist mixing. Energy has to leak through these steps instead of rushing straight out. Overall, the interior cools and transports heat less efficiently than it would if everything worked perfectly homogeneous. That slower, more structured heat flow isn't an abstract detail. It feeds directly into how bright Jupiter is today and how much power it has to drive weather. Jupiter radiates 1.6 times as much energy into space as it receives from the sun, so more than half of the total power leaving the planet is coming from inside, not from sunlight. That excess is leftover formation heat and energy from slow gravitational contraction, as Jupiter very gradually shrinks and releases potential energy. All of that energy has to work its way through the metallic hydrogen and fuzzy core regions before it can reach the weather layer. If the interior were perfectly mixed and convection were extremely efficient, Jupiter would have lost that energy faster and cooled more quickly. Its present internal heat flux might be lower. Its weather might be less intense. The fuzzy core, with its heavy element gradient and layered convection, helps control the rate at which this internal energy leaks out. It acts like a regulator on the heat engine that powers the winds and storms. So when you look at those bands moving at hundreds of kilometers per hour or the red spots spinning faster than a jet airliner, you're not just seeing what sunlight does to a gas giant's atmosphere. You're seeing a system where the main fuel source is the planet's own trapped heat, rising from tens of thousands of kilometers below, filtered through a chemically graded interior, and feeding the jets that Juno finds reaching 3,000 to 5,000 kilometers down. This is how the visible face of Jupiter links back to the hidden heart. The outermost percent of the radius, the clouds and storms, are just the skin of a much larger machine. The engine sits in the inner 30 to 50% of the radius, where metallic hydrogen, mixed heavy elements, and composition gradients set the rules for how heat moves and how rotation and convection couple. Change the core structure, and over long timescales, you change the jet depths, the storm patterns, and even how quickly features like the Great Red Spot can fade or persist. In other words, Jupiter's weather is not just an atmospheric story. It's an interior physics story that reaches down into the fuzzy core. The bands and spots are the visible readout of processes happening under millions of atmospheres. The mixing that diluted the core is still influencing how much energy leaks upward to drive the winds you can actually see. And if the inner metallic hydrogen and fuzzy core layers are powerful enough to shape the jets and storms, they're also powerful enough to do something even more dramatic. They can turn the entire planet into a giant electrical generator, building a magnetic field so strong it dwarfs Earth's and carves out a magnetosphere larger than the sun. So the next step is clear. If the core and its surrounding metallic hydrogen layer control the heat engine, how do they also power Jupiter's magnetic monster? How extreme is Jupiter's magnetic field, and what does that have to do with the fuzzy core you just built in your head? At the cloud tops, Jupiter's global magnetic field, the main dipole component, is about 10 times stronger than Earth's field at the surface. That is already intense. But the real shock is the size of the magnetosphere it creates, the region where Jupiter's field dominates over the solar wind. On the day side, it can stretch out hundreds of Jupiter radii, and on the night side, it extends into a long tail that reaches millions of kilometers. The whole structure is literally big enough to swallow the sun. If you drop the sun inside Jupiter's magnetosphere, it would fit inside that bubble. On Earth, the dynamo that generates the magnetic field lives in the outer part of the iron core, molten metal moving under rotation and convection. Jupiter is different. The field is not made in a solid or molten rock core. It is generated in a shell of metallic hydrogen, roughly between about 20,000 and 60,000 kilometers below the cloud tops, around 12,000 to 37,000 miles. In that region, hydrogen is a dense, conducting fluid, moving under Jupiter's rapid rotation and internal heat flux. The fuzzy core sits just beneath or overlaps the inner part of this metallic hydrogen shell. That geometry matters because even though the dynamo is not literally inside the core, it sits right on top of it. So anything that changes the properties of the inner metallic hydrogen, composition, density, conductivity, flow patterns, can directly affect how the dynamo works. Earth's field is sensitive to how the solid inner core cools and how the outer core convects. Jupiter's is sensitive to how the metallic hydrogen interacts with the heavy element-rich fuzzy core underneath. In a perfectly clean metallic hydrogen layer, made almost entirely of hydrogen and helium, convection could be relatively simple, driven mainly by heat loss. But the fuzzy core scenario says the inner metallic hydrogen is not clean. It has heavy elements mixed into it, dissolved rock and ice material from the partially eroded core. That extra material changes the density profile. It changes how easily parcels of fluid can rise and sink, and it can change the electrical conductivity of the fluid. All of those factors feed into the dynamo equations. If the inner metallic hydrogen is more heavily loaded with heavy elements near the fuzzy core, convection there may be slower or more structured. You can get regions where flow is stronger, regions where it is weaker, and that uneven motion can produce an asymmetric magnetic field, not a nice, simple dipole centered on the planet, but something more complex, with strong flux patches, offset dipoles, and irregular features. That is exactly what Juno found when it mapped the field up close. Certain parts of Jupiter, especially near the equator on one side, show extremely strong, localized magnetic flux, while other regions are weaker. The field is lopsided in a way that points straight back to a complex dynamo region. The raw conditions in the metallic hydrogen layer also make it a very efficient generator. Pressures in that shell are in the range of tens of millions of atmospheres, and temperatures are around 10,000 to 20,000 Kelvin. At those pressures and temperatures, hydrogen behaves like a metal. Its electrons are mobile, and its electrical conductivity can exceed that of copper at room temperature. You do not need wires here. The entire shell is the conductor. Combine that with Jupiter's rapid rotation, one day in about 10 Earth hours, and the internal heat trying to escape through the metallic hydrogen, and you have everything a dynamo needs: a conducting fluid, rotation to twist flows into spirals, and energy to drive motion. The fuzzy core adds another ingredient: composition gradients and heavy element mixing that modulate where convection is strongest and how deep it can penetrate. That is how the interior structure you infer from gravity and composition translates into the complex field Juno actually measures. This is not just an oddity locked inside the Jupiter section of a textbook. Once you understand how a fuzzy core plus a metallic hydrogen shell can generate a field this strong and this asymmetric, you can take that same physics and apply it to other objects. Brown dwarfs, which are more massive than Jupiter but not massive enough to ignite hydrogen fusion, also have deep conductive interiors and strong magnetic fields. Many hot Jupiters, giant planets parked very close to their stars, show hints of intense magnetism through radio emissions and star-planet interactions. In those cases, a Jupiter-like structure, maybe scaled up or heated differently, is a natural starting point. Metallic hydrogen dynamos, influenced by composition gradients and fuzzy cores, can generate fields strong enough to strip atmospheres, channel charged particles, and power radio bursts. The details will differ, but the basic engine, conducting fluid over a graded, heavy element-rich interior, is the same type of machine. So Jupiter's core is not just controlling storms or gravity harmonics, it's sitting under a global generator that shapes the space environment around the planet, and, by extension, gives you a template for magnetism across a huge range of giant worlds. Once you see how the fuzzy core and the metallic hydrogen layer couple, you start to see that layout everywhere you look, from gas giants like Saturn to brown dwarfs to exoplanets skimming the edges of their stars. That naturally leads to a comparison question. If Jupiter's core is fuzzy and its metallic hydrogen shell runs a powerful dynamo, what about Saturn, Uranus, and Neptune? Do they follow the same pattern, or are they running different internal machines? And what does that say about how common fuzzy cores really are in giant planets? Is Jupiter a total one-off, or are fuzzy cores just what happens when you make a giant planet of real physics instead of textbook diagrams? Start with Saturn, because if Jupiter were truly unique, Saturn would be the place you'd expect to see a different pattern. It's smaller, about 95 Earth masses instead of 318, its average density is lower, and its atmosphere looks different. Muted bands, huge rings, less violent storms. For a long time, it was easy to imagine Saturn as Jupiter-light, with a smaller, neater, rocky core and a cleaner gas envelope wrapped around it. But updated interior models, especially ones that use Cassini gravity data and ring seismology, point in the same direction as Jupiter. Saturn also seems to have a fuzzy core, not a simple ball of rock and ice, but a central region enriched in heavy elements that extends over a large fraction of the radius. There is still a denser inner part, but above that you find a wide zone where hydrogen and helium are mixed with heavier material in a gradient. So again, no razor-sharp line that says core ends here, just a smooth change in composition with depth. The key difference is scale. Saturn is less massive, so the pressures and temperatures in its center are lower than in Jupiter. But lower here means enormous. Central pressures are in the millions of bar, temperatures in the tens of thousands of Kelvin. That is more than enough for metallic hydrogen to exist, and for core material to erode and dissolve. The same basic processes, mixing, partial core erosion, composition gradients, can operate, just with slightly different numbers. So what you learn for Jupiter, that heavy elements can spread into an extended region and create a fuzzy core, carries over to Saturn. That means Jupiter is not a weird outlier. It's the extreme end of a trend that at least one other gas giant follows. Giant planets with thick hydrogen-helium envelopes naturally evolve toward graded interiors when you include realistic equations of state and long-term mixing. Uranus and Neptune push you into a different regime. They're smaller, about 14 and 17 Earth masses, and they have a much higher fraction of ices and rocks compared to hydrogen and helium. But even there, the simple solid core picture is breaking down. Models suggest their cores are only partially melted, and much of their interior is in exotic phases of water, ammonia, and other volatiles under extreme pressure. These ices aren't frozen the way you think of ice is. They're in supercritical or superionic states, where oxygen atoms may form a lattice while hydrogen ions move through it. It doesn't look or behave like familiar solid or liquid. For Uranus and Neptune, you don't talk about a fuzzy core in the exact same way as Jupiter, because the structure is more ice and rock-rich interior, plus a thinner gas layer. But the theme of high-pressure mixing still shows up. Heavy components can mix with lighter ones, layering and gradients can develop, and clean, sharp boundaries are again hard to maintain. The equations of state at those pressures and temperatures are still being refined, but the picture is already far from simple solid ball in the middle.
Pull all of this together and you end up with a spectrum instead of a binary choice. It's no longer core or no core, it's how mixed is the core and envelope, how graded is the interior. On one end, you could imagine a sharp, solid core with a relatively unmixed overlaying mantle and envelope. On the other end, you have something like Jupiter, with an extended, heavily mixed, fuzzy core that spans 30 to 50% of the radius. Saturn sits somewhere in between, with a fuzzy core but somewhat less extreme conditions. Uranus and Neptune occupy a different region of parameter space, ice giants, where weird high-pressure phases dominate, but with the same general trend away from clean textbook layering. Juno's data for Jupiter and Cassini's data for Saturn basically pushed you from a yes or no question to a continuous slider. You care about how strong the composition gradients are, how deep mixing goes, how many Earth masses of heavy elements got diluted into the fluid, and how much, if any, remains in a dense central seed. When you think about giant planet interiors now, you think about profiles and gradients, not just three-colored rings labeled core, mantle, atmosphere. This shift becomes even more important once you step outside the solar system, because exoplanet surveys have found huge numbers of Jupiter mass and Saturn mass planets at all kinds of distances from their stars. Some are hot Jupiters, roasting at a few-day orbital periods. Some are warm Jupiters, further out. Some are cold giants, more like our own. When you measure their masses in radii, some of them are surprisingly dense for their size, which implies large heavy element contents, tens of Earth masses or more. If fuzzy cores are already showing up in Jupiter and Saturn, the only two hydrogen-helium giants you can probe in detail, it is reasonable to assume that many of those dense exoplanets also have extended, mixed interiors, not neat, untouched rock balls hidden inside gas. You can use the Jupiter picture as your mental template, scaled up or down with different temperatures and irradiation levels, but following the same basic rules. Solids accreted during formation get at least partly dissolved, composition gradients develop, and the core becomes a region, not a hard object. This matters for more than structure diagrams. An exoplanet with a fuzzy core will cool and contract differently from one with a clean, compact core. It will move heat and heavy elements differently. Its magnetic field strength and geometry will differ, and its influence on nearby planets may change slightly because of how its mass is distributed. When you study exoplanet populations, you're not just asking how many have cores, you're asking how many have Jupiter-like graded interiors, how many are more Saturn-like, how many are closer to ice giant-style structures, and you interpret their measured densities through that lens. So the pattern is clear. Jupiter is not alone. Saturn likely shares a fuzzy core architecture. Uranus and Neptune show their own brand of high-pressure mixing, and exoplanets with similar masses are almost certainly running variations of these interior designs. Once you accept that, your next question should be, how do we actually test the physics behind these interiors on Earth? How do we know our equations of state and mixing rules are right when the conditions inside these cores are far beyond anything we experience naturally here? How do you study matter at pressures and temperatures that would destroy any normal lab setup long before you could even turn a dial? To get Jupiter's core right, you need to know how hydrogen, helium, water, and rock behave at pressures up to tens of millions of bar and temperatures of tens of thousands of Kelvin. That is far beyond Earth's natural range, so laboratories push right up against their limits. They use diamond anvil cells to squeeze tiny samples between two gem-quality diamonds, and they use giant lasers and shock waves to blast materials for microseconds into regimes that get close to Jupiter-like conditions. In a diamond anvil cell, a speck of material, maybe hydrogen or a hydrogen-rich compound, sits between the tips of two diamonds. As you crank up the force, the pressure climbs into the megabar range, millions of times Earth's surface pressure, while you heat the sample with lasers. Then you probe it with another beam of light, or X-rays, to see how its structure and properties change. This is one way you chase the molecular hydrogen to metallic hydrogen transition, the same transition you believe happens around 20,000 to 60,000 kilometers inside Jupiter. Laser-driven shock experiments go after even more extreme points on the phase diagram. You fire a powerful laser pulse at a target that creates a shock wave that travels through the material, compressing and heating it for nanoseconds to microseconds. In that instant, the pressure and temperature can reach into the tens of millions of bar and tens of thousands of Kelvin range, similar to parts of Jupiter's deep interior. Diagnostic instruments watch how the shock moves, how the sample emits light, and how its density changes, giving you data points for the equation of state.
Even with all these tricks, you only hit parts of the relevant range, and only for short times. But every new measurement anchors the theoretical curves. You get a better sense at what pressure hydrogen becomes metallic, how compressible helium is, and how mixtures of hydrogen and helium behave. That information is essential because interior models need equations of state, formulas that tell you density as a function of pressure and temperature, to turn gravity data into a radial structure. Where experiments cannot reach, simulations step in. Supercomputer calculations, often using density functional theory and ab initio molecular dynamics, treat electrons and nuclei quantum mechanically and evolve them forward in time. You feed in a mixture of hydrogen, helium, water, and rock-forming components, and you ask, at a given pressure and temperature, what is the structure? What is the energy? How conductive is it? Does it mix, or does it separate into layers? These ab initio simulations act like a microscope for conditions you can't reach or hold in the lab. They give you predicted equations of state for metallic hydrogen. They tell you how hydrogen and helium mix or demix at certain depths. And they can tell you whether core materials like magnesium oxide, MgO, or silicon dioxide, SiO2, tend to dissolve into metallic hydrogen at Jupiter core pressures and temperatures or stay as separate solid phases. The answer from many of these studies is exactly what a fuzzy core needs. At 30 to 45 million bar and 20,000 to 30,000 plus Kelvin, MgO and SiO2 and similar components look at metallic hydrogen and do not stay neatly separated. They become soluble, at least to some degree. That means an initially solid rock core or infalling rocky planetesimals can gradually erode. Their material can leak out into the surrounding metallic hydrogen, spreading heavy elements outward and building the composition gradients the gravity data are telling you must exist. This gives you a coherent chain. Juno's gravity harmonics say the inner region is diluted and extended. Lab and simulation work say the main core-forming materials should indeed dissolve under those conditions. Formation models say Jupiter accreted enough solids to supply 10 to 30 Earth masses of heavy elements. But those three together, and a fuzzy core stops being a strange exception and becomes the natural outcome of the physics. But this is not finished. There are still serious uncertainties that haunt the models. Small differences in the hydrogen-helium equation of state, like exactly how compressible they are at a given pressure, or at what point they start to separate, can shift your inferred densities at depth, change the internal temperature profile, and alter how much heavy material you need to match Juno's gravity data. A tiny tweak in the EOS curves can translate into a change of several Earth masses in the estimated heavy element budget. Mixing behavior is another big unknown. How fast heavy elements diffuse through metallic hydrogen, how easily layers of different composition exchange material, and how stable composition gradients are over billions of years. All of that affects how far out the fuzzy region extends and how sharp or smooth the gradients are. Different assumptions about mixing can give you fuzzy cores that are more extended or more compact, even if they match the same gravity harmonics within the current error bars. That is why you still see papers debating whether Jupiter has more like 10 Earth masses of heavy elements or closer to 25, or whether the fuzzy region reaches half the radius or something smaller. They're not arguing about the basic picture. They all agree the core is diluted and extended. They are arguing over the fine details, which depend on physics at conditions that are still hard to pin down in the lab and on the computer. The fuzziness in the core is now mirrored by fuzziness in the exact numbers. From your perspective, watching this from the outside, you're seeing theory chase data in real time. Juno pinned down the gravity field so tightly that the old broad interior models got wiped out. Now, experiments and simulations are racing to catch up, to refine the equations of state and mixing rules until the models can squeeze through the narrow window Juno opened. Every new high-pressure experiment, every new ab initio run sharpens your mental picture of what is actually happening 30,000 kilometers under Jupiter's clouds. And even once the physics of hydrogen, helium, and rock mixtures at these extremes is nailed down, there will still be things you can only learn from space. The next obvious question is, with Juno still flying and new missions like JUICE and Europa Clipper on the way, what can future measurements do to tighten this picture further? And what are the biggest unknowns that even perfect lab work cannot resolve on its own? What can future missions still change about this picture, if Juno has already trashed the old textbook core? First, Juno itself is not done. It was never just a single-pass gravity mission. Its orbit has been evolving because of Jupiter's gravity and tiny pushes from sunlight, so over time, its closest approaches have shifted over different latitudes and even over some of the big moons. Every new close pass where the radio tracking is clean adds more data on gravity and magnetic field. Those extra measurements let you refine the harmonics, especially higher-order ones, and that fine-tunes the interior models. Even if the basic fuzzy core conclusion doesn't change, the exact size of the fuzzy region, the gradient in heavy elements, and the details of the dynamo region can all be tightened. As Juno swings over the poles and skims near places like Ganymede or Io, you also get better constraints on how Jupiter's field interacts with the moon's, how the magnetosphere is structured in 3 dimensions, and how the gravity field looks off the equatorial plane. All of that loops back into the core work because the more accurately you know the global gravity and magnetic fields, the narrower the range of allowed interior structures becomes. Even small improvements in J4, J6, or specific magnetic anomalies can cut away entire families of models. Then there are missions like ESA's JUICE and NASA's Europa Clipper. On paper, they are moon missions, JUICE focusing on Ganymede, Callisto, and Europa, Europa Clipper focusing on Europa. Ice shells, subsurface oceans, plume activity, habitability, that is their main goal. But every precise flyby they make, every time they track a spacecraft's motion through Jupiter's system, they are also measuring gravity and magnetic fields, both from the moons and from Jupiter itself. Those data help in 2 ways. First, they tell you how massive and differentiated the moons are, which feeds back into models of how the Jovian system formed, including how and when Jupiter itself grabbed enough mass and energy to shape their orbits and compositions. Second, precise tracking of spacecraft near the moons can give additional constraints on Jupiter's higher-order gravity terms, because the moons move through that field, indirectly tying their motion to the planet's interior. The more tightly you understand the whole system, the better you can say what kind of core Jupiter needed to have while those moons were forming and evolving. Even with all of this, some questions about the very center of Jupiter are still open, and they're hard ones. You can ask, does Jupiter have a tiny, dense seed core deep inside the fuzzy region? Maybe just a few Earth masses worth of material that is still relatively compact? Or is the mixing so thorough that the heavy elements continue to be graded all the way down to the geometric center? Current gravity and magnetic data cannot fully separate those options. Both can fit within the error bars if you adjust the equations of state and gradients carefully. To distinguish between those scenarios, you may need better high-pressure physics, tighter equations of state that tell you exactly how dense a given mixture should be at a given pressure. Or you may need a future mission designed to do seismology-style measurements, something that can detect normal mode oscillations of Jupiter, like the way you use earthquakes on Earth. Tiny periodic changes in the gravity or light from the planet that reveal where density jumps occur. That kind of mission would go beyond what Juno can do and could finally say whether there is a truly distinct solid seed core or just a continuously graded interior down to the center. Another open question is how fast the core is still evolving right now. Jupiter is not static. It's cooling and contracting slowly by centimeters per year, losing internal energy over billions of years. As it does that, the interior temperature profile changes, convective patterns can evolve, and heavy elements can continue to move, settle, or separate. Some models suggest that over very long timescales, a more crystalline, solid core might be growing slowly inside the fuzzy zone as temperatures drop and certain mixtures become less stable, while the outer parts of the fuzzy region slowly lose some of their heavy load. That means the diluted core you infer today is not necessarily the diluted core that existed 3 billion years ago, and it won't be exactly the same 3 billion years from now. You're catching Jupiter midlife, at about 4.5 billion years old, not at the beginning and not at the end. If someone could take the same measurements on a younger or older version of Jupiter, they might see a fuzzier, more mixed core in the past, or a more stratified, partially recrystallized core in the far future. From your point of view, all of this is a reminder that the current interior model is a snapshot, not a final state. Every extra piece of gravity and magnetic data from Juno's extended mission, every constraint from JUICE and Europa Clipper on the system's history, and every improvement in high-pressure equations of state has the potential to nudge that snapshot, maybe shrinking the fuzzy region a bit, maybe changing the heavy element total by a few Earth masses, maybe tipping the balance between small solid seed and fully mixed center. And that raises one more step up in scale. If the fuzzy core today is just one frame in Jupiter's evolution, what does that frame tell you about the very beginning, about the early solar system, the planetesimals, the disk, and the way Jupiter grew enough mass to shape everything from asteroid belts to Earth's water supply? In other words, if you run this story backward, what does the current look of Jupiter's core say about how the whole system you live in actually formed? How do rocks that fall on Earth today tell you when Jupiter's core started to matter? Meteorites, especially the really old ones, carry a timestamp in their chemistry. When you look at isotopes in different meteorite families, you see something strange. Early solar system solids split into at least two distinct groups, two populations that formed in the same disk but somehow stayed separated for a few million years. The most straightforward explanation is that a giant object formed early and acted as a barrier in the disk, blocking material from freely mixing between inner and outer regions. That barrier is almost certainly Jupiter, not a finished gas giant, but a growing one, and the heavy element budget you inferred for its fuzzy core fits right into that story. To end up with 10 to 30 Earth masses of heavy elements, Jupiter probably had to grow to tens of Earth masses very early, within the first few million years of the protoplanetary disk's life. That means by the time a lot of planetesimals and planetary embryos were still forming and colliding, Jupiter's core, fuzzy or not, was already there, already throwing its weight around. So when you hold a meteorite that belongs to one population or the other, you are indirectly seeing the effect of that early barrier. Material that formed inside Jupiter's orbit followed one chemical track. Material that formed outside followed another. And Jupiter in between limited how much they mixed. A massive core region loaded with heavy elements and surrounded by a growing gas envelope changed the pressure and density structure of the disk and created zones where traffic became one way or was cut off entirely. The timing matters because if Jupiter reached, say, 20 or 30 Earth masses early, its gravity would already shape where embryos could survive and where they got scattered. That influences the final positions and compositions of the terrestrial planets, including Earth. The details of the fuzzy core tell you how much solid material Jupiter had eaten by that stage, and that number feeds straight into models of how much leftover material was available for building the inner planets. Now think about what happens to the solids Jupiter actually accreted. In an old, neat core picture, a lot of the incoming planetesimals would plunge to the center and pack into a solid ball. The volatiles they carried, water, ammonia, organics, would mostly end up in that central store. In a fuzzy core model, many of those bodies get shredded and vaporized in the deep envelope instead. Their water and other volatile components mix into metallic hydrogen and are distributed through the inner regions. That changes how you think about volatile delivery in the whole system. If Jupiter's heavy elements and volatiles are mixed deeply, then a lot of the water and organics it accreted are locked into that fuzzy interior, not sitting in a cold, solid core ready to be released.
At the same time, because Jupiter became a barrier, some fraction of the icy material that might have gone inward instead got rerouted, scattered, or ejected. So the balance between what Jupiter keeps inside and what it prevents from reaching the inner system becomes a key part of the story of how much water Earth and the other rocky planets could get. Jupiter is not a passive wall either. A planet 140,000 kilometers across and 318 Earth masses does not just sit in the disk. It acts as a gravitational barrier and a slingshot at the same time. Small bodies that wander close enough feel its hill sphere, the region where its gravity dominates over the sun's. Their orbits can be bent, tightened, or completely ejected from the system. The exact threshold for those outcomes depends on Jupiter's mass and on how that mass is distributed, which ties back to the core and envelope structure. A more massive or more centrally concentrated Jupiter has a slightly different hill sphere and escape speeds than a less massive or more diluted one. Those details determine how efficiently it cleans up its surroundings, how many planetesimals it ejects to interstellar space, how many it scatters inward toward the inner solar system, and how many it captures into its own system as irregular moons or Trojan companions. The fuzzy core itself doesn't directly change orbital mechanics, but the heavy element mass it represents is part of the total gravity budget that sets how ruthless Jupiter was as a cleaner and bouncer in the early solar system. So when you run the clock back, the picture you get is very different from the old simple gas ball with a neat core story. In that older view, Jupiter was mostly an overgrown version of Saturn with a tidy rock center. Its main role was just big planet out there. In the newer view, Jupiter is a chemically stratified, evolving giant that formed early, accreted a large mass of solids, mixed them into a fuzzy core, and then used its gravity to reshape the disk, split planetesimal populations, and control which materials could cross the gap between inner and outer regions. That has direct implications for habitability. If Jupiter's early growth and fuzzy core tell you it grabbed a lot of icy material and blocked or redirected even more, then it also played a major role in deciding how much water and how many carbon-rich bodies could reach the region where Earth was forming. Too little delivery, and you might end up with a dry Earth. Too much, and you get a water world with very different surface conditions. Jupiter's interior is not just interesting for its own sake, it's tied to whether the inner system got the right balance of volatiles for a planet like Earth to have oceans and long-term climate stability. In that sense, the fuzzy heart of Jupiter is part of your origin story, not just the planet's. It set the initial conditions for the asteroid belt, influenced the reservoir of comets, and helped decide which building blocks were even available for Earth and its neighbors. Instead of a quiet, simple gas ball with a neat core, you now see Jupiter as an early, evolving monster whose mixed interior and growing gravity field controlled the flow of material through the disk, and indirectly, whether your planet ended up as a habitable world or just another dry rock. The last step is to pull all of this together into one clear mental image, layer by layer, so that when someone says Jupiter's core, you don't picture a rock, you picture the real thing, the vast, super hot, heavy element-rich region that Juno and all this physics have forced you to accept. So at this point, what does Jupiter's core actually look like, in your head, in one clean line? It's not a solid rock. It's a vast, super hot, super dense region of metallic hydrogen, loaded with roughly 7 to 25 Earth masses of heavy elements, spread across about 30 to 50% of Jupiter's radius, with no sharp edge where you can say the core stops here. The heavy material just gets more concentrated as you go down. Now, walk it from the outside in, layer by layer, in plain terms. At the visible cloud tops, pressure is around 1 bar, like Earth's sea level, and the temperature is about 165 Kelvin, roughly minus 108 degrees Celsius, about minus 162 Fahrenheit. You're in cold, thin air with ammonia and other gases forming clouds. Below that, for the first 20,000 kilometers, around 12,000 miles, hydrogen is mostly in its molecular form, still a gas or a compressed fluid.
Pressure and temperature are climbing, but it's not yet in the exotic metallic state. Go deeper than roughly 20,000 kilometers and you hit the metallic hydrogen region that extends down to about 60,000 kilometers below the clouds, so 12,000 to 37,000 miles. Here, the pressure is in the millions of atmospheres, and temperatures are in the 10,000 to 20,000 Kelvin range. Hydrogen has been forced into a metallic liquid. Electrons move freely, and the fluid conducts electricity extremely well. This is where the dynamo that runs Jupiter's magnetic field lives, a huge rotating shell of conducting fluid. Under that, overlapping the bottom part of the metallic hydrogen zone and reaching toward the center, sits the fuzzy, heavy element-rich region you have been building this whole time. Across the inner 30 to 50% of the radius, the fraction of heavy elements in the mix steadily rises, maybe peaking at something like 7 to 25 Earth masses worth of stuff heavier than helium, dissolved into the metallic hydrogen. There may or may not be a tiny, denser seed in the absolute center, just a few Earth masses across. But if it exists, it is wrapped in a long, gradual transition, not sitting under a clean boundary. The reason you can say all of this with a straight face and not as a wild guess is that a lot of completely independent lines of evidence all converge on this one picture. Juno's precise measurements of Jupiter's gravity field give you the harmonics, J2, J4, J6, and the odd ones. Those numbers do not match simple compact core or coreless models. They match a diluted, extended inner region. Juno's magnetic field mapping shows a dynamo that is asymmetric and patchy in exactly the way you expect if the metallic hydrogen shell is influenced by composition gradients beneath it. Juno's microwave data give you water abundances, and with other measurements, tell you the heavy element enrichment is real. On top of the spacecraft data, you have high-pressure experiments, diamond anvil cells, and laser shocks, showing where hydrogen turns metallic and how dense it gets. Ab initio simulations show that core materials like magnesium oxide and silicon dioxide dissolve into metallic hydrogen at tens of millions of bar and tens of thousands of Kelvin, so a compact rock core is not stable against erosion under those conditions. When you run interior models that plug in these equations of state and try to match all the observations at once, the solutions that survive look like the fuzzy core you have been describing, not the neat little ball you grew up with. To get a sense of how alien this environment really is, take one imagined step into that inner region. If you could somehow stand there, which you cannot, there would be no solid ground under you. Pressure would be in the tens of millions of bar, tens of millions of times what you feel at Earth's surface. Temperature would be tens of thousands of Kelvin, hotter than the sun's visible surface, and the material around you would be things you normally call rock or ice, behaving as electrically conducting fluids mixed into metallic hydrogen. There is no clear horizon, no simple surface, just a continuous transition into denser and stranger phases of matter as you go down. Everything is compressed into states that do not exist naturally on Earth. Once you accept that this is what a core looks like in a real gas giant, you cannot go back to the old binary idea of solid core versus no core. Every Jupiter-mass planet, every Saturn-mass planet you see in exoplanet catalogs, especially the dense ones with big heavy element contents, almost certainly hides its own version of a mixed, graded interior. Some will be more extreme, some less, some hotter, some more heavily irradiated by their stars. But the basic architecture, an extended region of heavy element-enriched fluid instead of a clean rock sphere, will show up again and again. Understanding Jupiter's fuzzy core is not just about one planet. It's your template for how giant planets really build themselves, how they move heat, how they generate magnetic fields, how they sculpt their planetary systems, and how they control the flow of water and other volatiles that can make or break habitable worlds. Once you have this picture locked in, every time you see the words hot Jupiter or warm Saturn on a plot, you know there's a strange mixed heart inside, doing the same kind of physics that Juno has just forced you to confront here. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.